In this example, we will look at methane, CH4. Here we have the Lewis structure for methane, and the next step is to write the electron configuration for carbon, which is He, 2s2, 2p2. So we see that we have 4 valence electrons on carbon. 2 of those valence electrons are located on the 2s atomic orbital, and the remaining 2 electrons are located on the 2p atomic orbitals. So next, in order to create our sp3 hybrid orbital, we will take the 2s atomic orbital as well as all 3 of the 2p atomic orbitals on carbon. So taking those 4 atomic orbitals, we will combine them or mix them to form 4 sp3 hybridized orbitals. It's important to note that both the shape and orientation of our hybridized orbitals differ from the original atomic orbitals from which they were formed. And in this case, our 4 sp3 hybridized orbitals form the corners of a tetrahedron and are oriented 109.5 degrees from one another. Now, filling our hybridized orbitals, we see that our 4 valence electrons will fill so that we have 1 valence electron in each of the hybrid orbitals, as we would expect from Hund's rule. We can also see that the hydrogen atoms in methane are bound to carbon using the sp3 hybridized orbitals on the carbon atoms. And we can see that in the diagram here, where we see that the 1s orbitals on hydrogen form bonds with the sp3 hybridized orbitals on the carbon atoms. Okay? And the 4 sp3 hybridized orbitals on carbon adopt the tetrahedral shape with bond angle of 109.5 degrees. In this example, we'll look at the bonding in ammonia, or NH3. Here we have the Lewis structure for ammonia, as well as the corresponding 3D model, showing the trigonal pyramidal shape. The next step is to write the electron configuration for nitrogen, and we know that nitrogen is in group 15 of the periodic table, and by looking at the periodic table, we can write the electron configuration as helium 2s2, 2p3. So we see that we have 5 valence electrons in ammonia. Looking at those valence electrons in greater detail, in an atomic orbital diagram, we see that 2 of those valence electrons are located in the 2s atomic orbital, and 3 of those valence electrons are located in the 2p atomic orbitals. The next step is to create our hybridized orbitals by combining the 2s atomic orbital and all 3 of the 2p atomic orbitals. And doing so gives us 4 sp3 hybridized orbitals. So we see that our 4 sp3 hybridized orbitals are created from 4 atomic orbitals, the 2s atomic orbital and the 3 2p atomic orbitals. The designation sp3 simply indicates that our 4 sp3 hybridized orbitals were created from 1 2s atomic orbital and 3 2p atomic orbitals. Filling our orbital diagram with our 5 valence electrons, we will place the valence electrons in the orbitals as follows. So those would be the first 4 electrons, and then the 5th electron would be paired, pointing spin down. So we can see that in ammonia, the 3 nitrogen atoms are bound, 1 atom each, to each of the sp3 hybridized orbitals. And of course, the lone pair electrons, or the pair of non-bonding electrons, are also located in the sp3 hybridized orbital. Okay? So the lone pair on the nitrogen occupies an sp3 hybridized orbital. And this is what gives us the trigonal pyramidal shape. In this example, we look at the bonding in water, or H2O. Here we have the Lewis structure for water, as well as its 3D model. The next step is to write the electron configuration for oxygen, which we know is located in group 16 of the periodic table. And looking at the periodic table, we can write the electron configuration as helium 2s2, 2p4. So we see that oxygen has 6 valence electrons. And looking at those valence electrons in greater detail in the atomic orbital diagram, we see that 2 of the electrons are located in the 2s atomic orbital, and the remaining 4 valence electrons are located in the 2p atomic orbitals. And the next step is to create our hybridized orbitals, and we'll do that by combining the 2s atomic orbital and all 3 of the 2p atomic orbitals. So that's 4 atomic orbitals that we start with, and we mix or combine them to form 4 sp3 hybridized orbitals. Now you'll note that the 6 valence electrons are placed in the hybridized orbitals as follows: 1, 2, 3, 4, 5, 6, based on Hund's rule and the Pauli exclusion principle. So we can see from this orbital diagram, that the hydrogens are bound to the oxygen through the sp3 hybridized orbitals on the oxygen. Each one of the hydrogen atoms is bound to the oxygen through a different sp3 hybridized orbital. We can also see that the lone pair electrons are also occupy the sp3 hybridized orbitals, which gives water its bent shape.